So to start off Unit 2, we're going to talk about the history and the development of what we know about atomic structure. And I have a little timeline here to kind of give you some dates just for some reference for how long there is between some of these discoveries and actually kind of how long it's been since we've made another discovery about the atom and its structure. But I'm never going to ask you about these dates, but these are the people we're about to be talking about. And as we focus on each person, I'm going to have kind of 3 bullet points that you need to write down. And you can summarize the information that I'm giving you on that slide, but you need to make sure you're responsible for knowing what each person discovered, what kind of experiment they did, kind of how they did it a little bit, and then what they discovered about the atom and kind of how it's structured. And I might draw some pictures, or you can use your words to describe it, but you're responsible for understanding that new model of the atom and what it looks like. So our very first ideas about the atom actually came from ancient Greece, this guy called Democritus. And he actually was the guy that came up with the idea of an atom, except in ancient Greek it was called atomos. And that was just the idea that there is an indivisible, smallest unit of matter, now called the atom. So atomos actually means uncuttable, meaning that you cannot break it down past that point. Everyone else of the time thought that maybe if we had better technology, better cutting devices, you could keep cutting something down forever, just keep making it smaller and smaller. He never really did any true experiments. Remember, this is ancient Greece, but he based his ideas on kind of everyday observations, that everything was made of smaller and smaller parts. And so he figured that there would be a point where we just could not possibly cut something down any farther, that there was going to be a smallest uncuttable or unbreakable piece, and he called that atomos, the atom, basically. And so, like I said, you can kind of cut a piece of clay or a rock or a shell or a piece of cheese in half and in half again and in half again and just keep cutting it. But he thought and kind of figured there was a point where you would never be able to cut it. And that's what he called the atom. So he thought that atom, whatever that smallest bit of matter was a solid homogeneous sphere made of that original substance. So if you were cutting or breaking a shell down, then you'd end up with a teeny tiny little particle of a shell that was an atom of shell. And then there was a teeny tiny stone particle, the uncuttable teeny bit of stone that you could get down to was just a solid little sphere of stone or cheese. Whatever the substance was, he thought the atom was the same stuff. It was just smaller. Now, it might seem a little bit silly these days, but that's all that his technology could really discover. And so he started off our journey of the atom. And this was way, way long ago. It actually took a long time for anyone to develop anything more about what the atom is and how they work. So, enter Mr. Dalton. And Dalton came up with some rules about atoms and how they act. And that's what we're going to be writing down here by these 1, 2, 3, 4, 5, the rules on how atoms act in general. And he derived these rules by studying how gases act and interact with each other. Now, Mr. Dalton didn't actually develop any new model of the atom. He didn't develop anything new from ancient Greek times. He's still assuming that atoms are solid, homogeneous spheres, just like Democritus did. But he did help us understand a little bit more about the atom, which led to some further discoveries. So his first rule about atoms was all matter is composed of atoms, small particles and pieces. And all atoms of the same element are exactly the same. Atoms can't be created or destroyed. They're indivisible, coming back to that idea of uncuttable or unbreakable atoms that Democritus came up with. That atoms combine in whole number ratios, kind of like H2O is H with 2 H's, 1 O, not H2.5, O, 1.2. It's always going to be whole number ratios that they combine in. And in reactions, atoms only rearrange. They're not created or destroyed, coming back to that number 3. They just separate from each other and combine back in different places. And Mr. Dalton was actually pretty close to correct on 3 out of these 5 rules. So I do want you to write them all down, but you can put little checks by 1, 4, and 5 because those are still true. We still count on the fact that all matter is composed of atoms. They combine in whole number ratios, and they just get rearranged in reactions. But later in this video, on the next page, we're going to talk about some different examples of elements that aren't exactly the same as each other. And nuclear chemistry, now that we have that technology, can actually break down and destroy atoms, turn them matter into energy. So 3 out of 5 isn't bad. Now, later on, Mr. Joseph Thomson came up with the electron. So we were still thinking that atoms were solid, homogeneous spheres up until Thomson's time. And what he did, and that's what we have this little picture off to the side of, you don't have to draw this, is he shot cathode rays, which, if you know, it's kind of like an electron gun. They didn't know it was electrons at the time, but they just knew it was these beams of light. Cool, technology of the day. And so he shot these beams of light between magnets, and he noticed that this beam of light always bent towards the positive side. Even if he moved those magnets around, switched the positive and the negative, it always bent towards the positive. Turned them sideways, it always bent towards the positive. No matter where he put it, he saw the beam get attracted to the positive plate. So he realized, because opposites attract, they knew that much at that point, the beam must be made of something negative. And since the beam is coming out of, some gases and electricity, energy, that the atoms themselves must have some kind of negative piece to them. So that's how he discovered the electron. Now, technically, he called it something completely different, and the name's super weird, but that's what we know as the electron today. And so he incorporated these electrons into that kind of solid sphere. They call it the plum pudding model because he was over in England. Plum pudding's a thing over there. Over here in the US, I'd probably think of this as like the chocolate chip cookie model. That the whole atom is the cookie, with all of that dough being a positively charged, kind of mushy, well, he didn't think it was mushy, but a kind of dough surrounding these chocolate chips, which are the electrons. He just literally said, oh, there must be electrons in here, so he scattered them as little dots throughout the atom. We knew we had to have positive stuff canceling out the negative stuff because we'd never detected any charged stuff before, so it still had to cancel out. There had to be some positive stuff there to cancel out the negative stuff that he discovered, but he just kind of threw it all together. Called it the plum pudding model. Now, that is not what the atom really looks like, and Mr. Ernest Rutherford was a big part of developing our new kind of picture of the atom. What he discovered was the nucleus of the atom. If we were going to say he discovered an individual item, but really the concept or the idea that atoms are mostly empty space was his big discovery, that most of the area of the atom is empty and the mass is concentrated in a very, very small part in the center. And the way that he discovered that was by shooting some radiation at the most dense element known and easily kind of turned into foil. He took gold, rolled it into foil. So it was very, very dense, but very, very thin. And he surmised that this foil was probably very close together, single layer or two of gold atoms. So when he shot this radiation at it, if the atom was solid, like what we were thinking before, what Mr. Thomson had come up with, then these atoms in this radiation beam would bounce off of the solid atoms in the foil, because they're very dense. They'd be like a wall that it bounces off on. But because most of the radiation went straight through, that meant that most of that atom was empty space. There was mostly nothing for it to be hitting. Even though there were atoms lined up there like a wall, they weren't a solid wall. It was like a chain link fence. So most of the beam went through. Now some of it did hit stuff and bounce off. So there was stuff there to hit, but it just wasn't most of the space that the stuff could hit. So that's how he came up with, okay, there's something hard enough to have that nucleus bounce off, or the radiation bounce off of something. So he called that the nucleus, and then most of the atoms empty space. So this is what we call the nucleus model. There's a very small, positively charged nucleus in the center with electrons scattered around, and these electrons are really, really small, not big enough to really deflect. You can't even see most of the dots that I'm putting down. They're just scattered around in this space. That's not really a dot that I was trying to put in there. So the atom being mostly empty space, including that edge. I put a dotted line around that edge there to show that there's not a hard shell, there's not a hard kind of edge to our atom. Most of the atom is in that nucleus. Then Niels Bohr came along, and he was the one that actually discovered that the electrons aren't just randomly scattered around in that empty space. He discovered that electrons actually orbit the nucleus in what we call energy levels. So they're kind of orbits. We actually call them orbitals, but we also call them energy levels. And Mr. Niels Bohr did one of my favorite experiments, and we're actually going to have a chance to recreate some of what he did with a little bit less calculations. He burned different elements into compounds and saw the light, the pretty colors that were produced from those elements and compounds. Now, he took very precise measurement of the energies of that light, and so he did a lot more work than just, pretty colors. But what he did when he was looking at those spectra, the different types of light that was produced, is he saw that only certain colors were produced. If you look at the kind of rainbow lights that I have up there, there's very specific beams and kind of lines in that spectrum where we see colors. And he looked at lots and lots and lots of elements, and he realized that even though, one element might have a different spectrum, a different set of lines than another, there were some certain characteristic lines he saw a lot of, but then there were some certain places he never saw lines. So because we knew that the light came from electrons, that was something that we discovered all the way back from Thomson and his experiments. So he knew the light comes from electrons. So if the light only has certain energies that are produced, that must be the electrons only have certain energy levels they can be at. So kind of fancy math going on there, but he developed what we call these days the planetary model, where we have electrons orbiting the nucleus in stable orbits, kind of like how planets orbit the sun. So a lot like Mr. Rutherford's model, except now instead of just a big empty space where the electrons are scattered, they're actually orbiting, moving in predictable orbits. Now, Mr. Heisenberg came along, and he completely disagreed with Bohr. And actually, a lot of other scientists were realizing that Bohr's experiment worked for some of the simpler elements, but it didn't actually work for more complicated elements, that their electrons weren't at as precise energy levels as we thought. So Mr. Heisenberg actually discovered that electron orbits are not predictable. He came up with what's known as the Heisenberg uncertainty principle. We'll talk more about that in just a moment. And Mr. Heisenberg, kind of like Mr. Bohr, used math to do most of his calculations. He didn't do fancy, electron guns and setting stuff on fire. He actually used matrices and invented new math to do quantum mechanics, but he basically managed to prove that you can never know a particle's exact position and momentum at the same time. And momentum is kind of like energy. Your physics teacher will tell you a lot more about that. But if we know kind of the energy level an electron's on, we can't actually know exactly where it is, which means that we can't have these nice, neat orbits where electrons are going round and round in little bitty circles, because then we would know its energy and its momentum, and he proved we can't. So we can't know its position and its momentum at the same time. It's just impossible. So what that meant for the atom, and you actually have this little diagram drawn there of the electron cloud model in your packet. He turned what were neat orbits into just some general cloud-like areas of probability where you are most likely to find an electron. But it's not just a ring, let alone an orbit, that is going around in nice, neat little circles. And we're going to talk more about these shapes later, but they're not always necessarily spheres and nice rings either. Some of these look kind of weird shapes, which is where that word electron cloud comes from, because it's kind of poofy like a cloud. So these are only the most likely places where you're going to find an electron. I think they generally integrate to like 95% likelihood, but you never really know exactly where it's going to be at in these areas, just somewhere around in those areas. So the key thing to take away from this is that science is a process of learning, understanding, and discovering new ideas. All of these people were at the peak of technology for their day, but as technology developed, our understanding of the atom developed as well. So this electron cloud model is actually kind of old. It's almost 100 years old, and maybe in the next 5, 10, 100 years, we might actually develop a better model, understanding more and more about how the atoms put together. You, your kids, or grandkids might look back at some of these models, even this Heisenberg uncertainty principle, and kind of scoff and say, oh, how silly they were. It's just a matter of technology and perspective. So that finishes out our first page of notes here. And in class, just kind of FYI, we're going to take a little bit of notes on page 2 as well, but the questions about atomic history and structure are here on page 3, questions 3 and 4. So if you wanted to work on this, especially if you're watching this in class, those could be the problems that you watch along with this, that you complete along with this. So you could pause this now, complete those problems, and then move forward to the page 2 notes if you'd like. So moving on to page number 2, I'm going to get a little bit more specific about this atomic structure that we know. We're going to talk about those things we've discovered: electrons, protons, neutrons, all the parts of our atom in terms of their mass, charge, symbol, and location. And you notice I've made a table here, which I think is the best way to organize this information so that you don't have to write mass, charge, location, symbol over and over again, but you are welcome to organize it however you'd like, as long as you get that information about each of these pieces of the atom. And if we start with electrons, an electron actually has no mass. We say 0 AMU. AMU stands for atomic mass unit. It actually does have a very, very, very tiny mass, but it is so tiny it's almost unmeasurable. Now, its charge is, I'm going the wrong direction. So, if we're talking about mass, let's finish out the mass for all of them. Protons have a mass of 1 AMU, 1 atomic mass unit. That's not 1 gram, but we literally just defined what 1 proton and 1 neutron weigh, which, spoiler alert, neutrons weigh 1 AMU. And instead of having to deal with crazy scientific notation number, because this is still a very, very small amount, these are very, very small items, they just defined whatever they weigh as 1, so we can talk about them with some more normal numbers instead of crazy tiny numbers. So if we move on to charge now, an electron's charge is negative, and I do want you to write -1 there, because a proton's charge is positive, and it is the equal amount of charge as an electron, just a positive charge. So these charges are equal and opposite. Some people have the misconception that because an electron is so tiny, that its negative charge is also tiny. But these are exactly the same amount of charge. They're just opposite. Electrons are negative, protons are positive. And neutrons, what we call neutral, they have no charge. Now, as we talked about in our history, electrons exist outside of the nucleus in what we call the electron cloud, and our protons and neutrons both exist inside the nucleus. Now, the symbol is kind of an afterthought, but this is going to save us a lot of time. Instead of having to write the word electron over and over again, the symbol for an electron is just a lowercase e with a little negative sign on it. In fact, each of these symbols is just the first letter of the name with the charge of that particle up in the top corner. So neutrons are N0. So these are going to save us a lot of time. You're definitely going to see me use these, especially later on this page and in some of our practice problems, just to save time. You're welcome to use them anytime in replacement of those full words. So we said that protons and neutrons are both in the nucleus together, but how would all of those positively charged protons exist so close together if there's nothing negative to cancel them out and to attract them? Because usually like charges repel. Well, that's what we call the strong nuclear force. Really, it's one of the 4 basic forces in nature. You don't have to write all this blue stuff down. It's like gravity, or the electromagnetic force, the fact that opposites attract. It's just another type of force that exists that we know has to be there, because otherwise that nucleus wouldn't be able to be held together. Now, some important words to define. We're going to start talking about something called isotopes, and we're actually going to define isotope in a moment. But all of these words are going to be important for understanding what an isotope is. So first, atomic number. The atomic number is the number of protons in the nucleus, which is unique for every element. When you get your periodic table, which hopefully you already have, that's going to be that top number in the element square. Hydrogen has an atomic number of 1. The mass number for an element is the total number of protons and neutrons in the nucleus. And that's counting protons and neutrons, so that's always going to be a whole number. Lots of people think that that number underneath the symbol is the mass number. That's actually the average atomic mass. We're going to talk about that, calculate that later. But it's not the mass number. The mass number, we literally just count the protons and the neutrons and add them up. It will always be a nice whole round number. Isotopes are atoms of the same element that have different masses. And because the mass of an element comes from protons and neutrons, one of those has to be different to give us a different mass. But if we're the same element, that means that our atomic number, our protons, have to be the same. So, isotopes have the same number of protons, but a different number of neutrons. Ions are similar, but ions are atoms of the same element that have different charges. If you remember up top, the charged particles are protons and electrons, so one of those has to be different to give us those different charges. But if those are the same element, just like isotopes are the same element, that means the protons are the same, which means the only thing that can be different to give us a different charge are the electrons. So we're going to do a lot of more detailed practice with isotopes and ions later on. But it's important that we know what they are, because these are some of the key differences, like Mr. Dalton's atomic theory. He thought that all atoms of the same element were exactly the same. We now know there's such things as isotopes and ions, where they are the same element, but they do have some different stuff happening with them. So, two last things on this page. You have two different ways to show how many protons, neutrons, and electrons are in a certain atom. And the first one is really the more useful one. It's called the nuclear symbol. That takes all of the important numbers for an atom, the mass number, meaning the protons and the neutrons added together, and the atomic number, and we put them in the top left and the bottom left corner of the element symbol. Kind of like this, 4/2 He. And that symbol is going to help tell people and identify all of the protons, neutrons, and electrons in an atom. We're going to have to do that on page 4 a little bit, so I'm going to walk you through that process. If we're looking at this nuclear symbol and we want to find its protons and its neutrons, the first number to start with is the atomic number, that bottom number. It is the foundation of this nuclear symbol and which element we've got. So if that's a 2, that means that we have 2 protons. Then that top mass number is the protons plus the neutrons. And so if we're trying to find our number of neutrons, you can kind of think of it almost like a little subtraction problem. 4 total protons and neutrons minus the 2 protons we know we have means that this atom has 2 neutrons as well. If we look at another example, 7/3 Li, we have 3 protons because that bottom number always tells us our protons. Then if we subtract the mass number minus that atomic number, 7 minus 3, tells us this atom has 4 neutrons. They're not always the same as each other, but they're generally pretty close to each other. I would be pretty worried if we ended up getting like 10 or 20 neutrons when we just have 3 protons. But let's try putting together a nuclear symbol if we start with the number of protons and neutrons. I would always start from that foundation, that bottom atomic number, which is the number of protons. So I'm putting a 5 on the bottom. Then remember, the mass number is the protons plus the neutrons. So here we just add 5 plus 12, that's 17. And then to find the element symbol, we actually need to go look at the periodic table. And because this element has 5 protons, its atomic number is 5, we're going to go look at square number 5 on the periodic table and realize that's boron with a B symbol there. So 17/5B is our element symbol. Quick note, even though we've got numbers over each other, these are not fractions. Do not write a line here. That does not happen. So it is just hovering numbers kind of in the top and bottom corners around the element's symbol. Now the other notation that we have for describing an element and the different isotopes we can have is called hyphen notation. And this is where we just take an element's name or symbol and then we put a hyphen. That's what this little dash is here. And then we just write the mass number after it. It's pretty simple, but it doesn't necessarily give us as much information as that nuclear symbol does. So if we take that same first example that we already wrote down, you can choose whether you write it or not, but we're just going to turn this into hyphen notation. Well, what is the name of element He? Well, that's helium. Then what is the mass number? Remember, the mass number is the top number on our nuclear symbol, so that's 4. So sometimes we do this because it's a lot easier to write out than getting it into that fancy notation, especially with like typing these days. It's easier to type helium-4 than 4 over 2 He. If we do the same for that 7 over 3 Li, what's the name of Li? Lithium. Then, of course, a hyphen in our hyphen notation, and then our mass number is 7. So it's pretty easy to go from the nuclear symbol to the hyphen notation. But let's go ahead and try and put one together, find our protons and our neutrons from the hyphen notation. So if we're trying to find these number of particles, we actually have to start. Before we can do anything, we can't see that proton number. We don't have an atomic number labeled in this. We actually have to take that name chlorine and go look at the periodic table. Find chlorine. It's over there near the right side of the periodic table. And then we can see its atomic number at the top of that square is 17. So it's a nice short notation, but we have to have a periodic table to be able to find some of the important numbers for our atom. Now, because we have our mass number here, this is chlorine 35, we know that our protons plus our neutrons is going to equal 35. So if we're trying to figure out how many neutrons we have here, we can do 35 minus 17, and that gets us 18. So hopefully these notations make a little bit of sense, and you're going to be doing a little bit more of that on page 4. We got one last key idea here. The word neutral. I used that earlier when I was talking about neutrons, meaning that they have no charge. An atom as a whole can be neutral if the number of protons equals the number of electrons, if the positive stuff is equal to the negative stuff. And if I give you a couple examples of a couple of notations, everything we've been seeing so far has been neutral. If something has a charge, it's going to have that charge written in the top right corner. Every corner has a meaning. Now, we're going to come back to this and spend a lot more time with ions, things with charges, later. But if I was looking to find our protons and electrons from this nuclear symbol, and everything on page 4 is neutral, then the starting point is to find our protons, which is 3. And then if it's neutral, then the protons are equal to the electrons. So our electrons here are 3 as well. What's different and special when we have a charge isn't the number of protons. We still have to have 3 protons here because our atomic number for this lithium is still 3. But if we have a positive charge, meaning we have more positive protons than negative electrons, that actually means we have 1 fewer electron. So that would be 2 electrons. Don't worry about those ions, those charges too much. We're going to come back and spend a whole day on that later on. So at this point, you can fill in questions 1 and 2 at the top of page 3, and then the really kind of big task here is practicing with our notations and finding those protons, neutrons, and electrons, mass numbers, everything on page 4. So I actually have a separate video going over page 4 stuff just so that this doesn't end up being super long. You might be able to figure out a lot of that yourself, but if you end up getting stuck or if you have trouble getting started on page 4, go check out that video.